Right, so we're getting into Unit 2, which we'll be discussing bonding and then what that has to do with structure of substances. So in terms of types of chemical bonds, first thing we have to understand is what a chemical bond is. It's just an attraction between the positive nucleus of one atom and an electron in the other atom. And so that's going to hold atoms together in a number of different ways, which depends on electronegativity or ionization energy, or at least can be explained by electronegativity or ionization energy. So if I have a sodium chloride ionic bond, we think of that as a transfer of electrons from the sodium, which has a low ionization energy, to the chloride, which has a high ionization energy. And both of those are just to say that the sodium atom has a less positive or larger nucleus, and therefore that electron or those electrons are less attracted to the sodium. And so we say, because the difference in electronegativity is so big between sodium and chlorine, that the electron is simply transferred from the sodium to the chlorine to make a chloride. And then once that transfer happens, the sodium is still attracted to that electron in the sense that it's attracted, we say the positive sodium is attracted to the negative chloride ion. But it's because that chloride ion has an extra electron, that's the thing that makes it negative, and that's the thing that makes the sodium attracted to it. And so we could really still say that the sodium is attracted to an electron because it's attracted to a negative ion, and the negative ion is negative because it has that extra electron. And then a covalent bond is simply where both atoms, usually non-metals, right, are both have such high ionization energy that they will, neither of them wants to lose an electron very easily, and so they end up sharing in order to complete their outermost s and p orbitals. And so that's a covalent bond. Co meaning they both have these electrons. They both the electrons in that overlapping area belong to both the hydrogen and the oxygen in this case. And then the last type is metallic bonding. So if both atoms are metals and they tend to be large, they tend to have less positive nuclei than their non-metal members of the same row. And so that means that the electrons in the outermost shell of those metal atoms are not super attracted to the nucleus, and it makes them mobile, makes them free, allows them to break free of that particular atom, and it creates what's called a sea of electrons just floating around within a sample of iron, let's say. And those positive nuclei are then going to be attracted to that sea of electrons that is created by having these delocalized or free moving electrons from each of those iron atoms sort of having a loose association with its valence electrons. So we call that the sea of electrons model. Within covalent bonding, which of course is the sharing of electrons in order to achieve an octet, this is usually going to be between two nonmetals because, as we discussed, they both have high ionization energies. So, for example, if I have a phosphorus trichloride, both the phosphorus and the chlorine have a high attraction for their valence electrons. Neither of them are going to easily lose them, and so we end up with these lines being drawn to indicate sharing. So the bond itself is considered a mutual attraction of the two nuclei for those shared electrons. So this bond, like let's see here on the bottom, is just that the positive phosphorus nucleus and the positive chlorine nucleus are both attracted to those two negative electrons in the middle. So they have that mutual attraction. So the more electrons are being shared, meaning like a double bond or a triple bond, the greater that attraction is going to be that the positive nuclei feel, and therefore that's going to pull those positive nuclei closer to those bonding electrons and make a shorter and stronger bond. So if we compare a Cl2 molecule, that's just a single bond. There's only two negative electrons in the middle between these two chlorine atoms. We compare that to an O2 double bond, that's 4 electrons, and so there's going to be more attraction, and you can see the nuclei moving closer and closer together. All right, so a review on drawing Lewis structures. A couple of steps here. Whenever we're given a molecule, we want to determine the total number of valence electrons that we have in that molecule. Draw the skeleton structure, and you'll see an example of that in just a second. Connect all the atoms to the central atom with single bonds. Complete the octets of outer atoms first. And if need be, you're going to double or triple bond. That just basically means if you run out of electrons, but you still have atoms that are not yet at a full octet. So here's an example of a couple of Lewis structures that we've followed those rules. We've got our skeleton structures. We've only used the correct total number of valence electrons from the periodic table. So for example, carbon is in group 14. It starts with 4. Oxygen's in group 16 and starts with 6. So we have 6 plus 4 is 10 plus another 6 is 16, and we've only used 16. Okay, so we had to double bond here because we ran out of electrons, but carbon didn't have enough. This other example over here is what it's showing us is that we can follow rules 1 through 5 and using those 16 electrons make all 3 atoms obey the octet rule but not get the right molecule. So how do we know that we didn't get the right molecule? And the answer is we evaluate formal charges. So formal charges are basically just sort of a math trick that we do to figure out which Lewis structure is the most likely to be correct. And so if I look at the double bond scenario here, my valence electrons that I originally had for oxygen and carbon were 6 and 4 respectively. And so what I've done is just written those down, 6 and 4 and 6 right below the atom. And that's just looking at the periodic table and what group they sit in. Then I'm assigning electrons to those atoms based on this Lewis structure. And the way that I assign them is the electrons that are not being shared get assigned completely to that atom. So if we look at the 4 little dots around this left-hand oxygen, those 4 electrons belong 100% to just this oxygen atom. But if I look at the 2 lines, the double bond in the middle, those 4 electrons that are part of that double bond are being shared by oxygen and carbon, so I'm only going to assign half of them. So like that vertical line you can think of as splitting the double bond in half. And so instead of all 4 electrons being attributed to oxygen, just 2 of them are. Okay, so then if I look at these 4 plus half of the double bond, so that's 4 plus 2 is 6. And so I have 6 electrons assigned to oxygen. And then 4 would be assigned to carbon and 6 more would be assigned to this oxygen. And when I subtract the original valence electrons for each atom minus the assigned electrons, in this case I get all zeros. That's good. We want the formal charge to be equal to 0 unless it's a polyatomic ion, in which case we want it to be equal to the charge of the ion. But for most molecules, it's going to be 0 is best. Over here, this other possibility that works in terms of the octet rule results in 7 being assigned to this left-hand oxygen and only 5 being assigned to this right-hand oxygen. And so when I do my subtraction, I get non-zero answers, -1 and +1. And so those are going to be less likely, and therefore this is a less likely Lewis structure to be correct for this molecule. Okay, and then the last step is if there is what we call resonance, we want to identify that. And resonance just means when we do have a molecule with, like, let's say a double bond, single bond situation, and in this case, because it's ozone and they're all 3 oxygen atoms, it's not like the CO2 scenario where there's 2 different ways to draw them and they come up with different formal charges. Here, these are both just as good as one another. So we draw it actually both ways, and we do the little double arrow in between to show that this molecule could be, looked at it in either direction, either way. Another thing to think about here is usually with a molecule like this, the experimental data shows that it's not really a double bond, single bond, but instead two equal bonds that are sort of an average of the two. So rather than having a double bond and a single bond, and having this bond distance be shorter and this one be longer because it's only a single bond, we actually have like two 1.5 bonds in reality. And so that's something to keep in mind when we have resonance. Okay, polarity. So anytime we have an unequal distribution of electrons across a bond, we have a polar bond. And so here you can see, kind of visualize an F2 molecule where both atoms are very electronegative. They're both pulling with great force, but equal force. So the difference in electronegativity between two fluorine atoms is 0. Both of them are 4. Okay, and so this green distribution, throughout the molecule just simply means the electrons are spending equal time on both sides of the bond. Whereas the HF molecule here, it's very blue on one end, which means that's the hydrogen end, which isn't as electronegative, and then very red and orange on the fluorine end. So that's telling you the electrons are being pulled, and that's going to be the partial negative end of the bond. So that's going to be a very polar bond. Even more polar would be like lithium fluoride, which isn't even considered a covalent bond. It's considered ionic because the electronegativity is so different and the electron density is so different that we in fact just say that the lithium has lost an electron and the fluoride has gained one. So, but it really, there's a lot of shades of gray as we work from non-polar covalent all the way to ionic. Generally we say it's a metal non-metal that makes an ionic bond, but really what it comes from is a big difference in electronegativity between the two atoms. Okay, then we want to talk about potential energy. So what's going on here as two atoms come together? So these are two hydrogen atoms, and when they're far apart, they're so far apart that the two nuclei, which are both positive, don't really repel each other because they're too far apart. But at the same time, the electron from this atom is not necessarily going to be super attracted to the nucleus from this atom, which is what would have to happen for them to bond. But if they come close enough together, so here we're looking along the x-axis at distance. So as these two atoms get closer and closer together, all of a sudden the energy is going to change a little bit. And so what we see here is the potential energy, which is the y-axis, drops as the nuclei get closer to the electron of the other atom. And that's because they're losing energy because they're gaining stability, because positive wants to be close to negative. And so the positive nucleus from this hydrogen atom is getting closer to that negative charge on the electron in the other atom. And then there's a minimum energy that they reach, which is way down here at the bottom of this trough, and that is the most stable distance between the two nuclei. So that's what we're measuring here, is the distance between two nuclei. And so at this distance, each hydrogen nucleus is happy because it's as close as it can possibly be to the electron of the other atom, which it is attracted to, while not being too close to the proton of the other hydrogen atom. And so you can see what would happen if you pushed them too close together. The potential energy would skyrocket because now you're putting two positive nuclei too close together. Okay, so let's look at an example question that we took from the video number 2 from section 2.2 in AP Classroom. So it says, this is an example or released item. The potential energy diagram given for a C triple bond O is what we see here. It says a student claims that the curve for a CO single bond would be less steep and would be shifted to the right compared to this curve. Do you agree with this claim? Why or why not? So think about those two things. Do you agree? And explain yourself, and just kind of pause and think about that for a second. Okay, so hopefully this will make sense. Yeah, I would agree with this person. So I would agree that if it were a single bond, two things would be true. Number one, a single bond only involves two electrons, which means the attraction would be less, and so the potential energy dip would be less. Okay. And also the bond length would be greater. So single bonds are longer because the attraction is less. And so the the distance between the two nuclei at which we have the bottom of the trough here, the most stable point, the distance would be greater for a CO single bond compared to the distance to the bottom of the trough. I'm sorry, the distance between the nuclei where we have the bottom of the trough, if it's a CO triple bond. So triple bonds are very stable and they're very short. And so that's what we're showing here with this graph. Okay, the last thing we need to talk about is ionic bonding. And an ionic bond is just the electrostatic attraction that we create when we have a positive ion that's lost an electron and a negative ion or anion that's gained one. So here we see a crystal here, it could be a salt crystal. If we think about Coulomb's law, we have two things really that are affecting the strength of this ionic bond. We have the difference, in charges, all right, just like we talked about with like binding energy of electrons to the nucleus of an atom. This is referring to the force of attraction between an entire cation and an entire anion. So if the charge is +3 versus -3, that's a huge difference in charge, and so we're going to have a really big force, a really strong force of attraction within that crystal. And then of course if the radius is smaller because it's in the denominator, that means that our force is also going to be greater. So therefore we could say attraction increases with greater charges. So like aluminum nitride would be +3 and -3 compared to sodium chloride, which is only +1, -1, and smaller distances. And this means a greater attraction is going to result in properties such as lower solubility, because it's going to be a lot harder for water molecules to pull apart aluminum nitride, where the charges are so different and the attraction is so great, than for a water molecule to pull apart sodium chloride, where the charge is not that different, +1, -1. And then also the smaller the ions are. So like lithium fluoride are very small. So even though they're only +1, -1, you might have a higher melting point or a lower solubility simply because the lithium ions and the fluoride ions are so small.